Hello, my paper is about finding an efficient set encoding for the Hamiltonian cycle problem. The Hamiltonian cycle problem, HCP in short, is one of the well-known NP-complete problems. Given a graph, directed or undirected, the goal of the problem is to find a cycle in the graph that includes each and every vertex exactly once. Since HCP occurs in many combinatorial problems, CP systems provide a global constraint named circuit for the problem. Given a graph G represented by a list of domain variables, an assignment of these variables satisfies this constraint if the assignment represents a Hamiltonian cycle. So for example, for this graph, this assignment 2, 4, 1, 3 satisfies the constraint. However, the assignment 2, 1, 4, 3 does not satisfy the constraint because this subgraph contains two subcycles. We begin with Minizinc's Decomposer, which uses a position variable for each vertex. The generated constraints ensure that all the problem variables are distinct, all the position variables are distinct, and the positions are connected into one cycle. This encoding does not perform well. It can only solve the Knight's-Tour problem for size 8. The Dantzig's IP model is well known for HCP. It uses a matrix of Boolean variables H. Hij equals 1 if the arc ij is in the cycle. It uses degree constraints to ensure that each vertex has exactly one incoming and exactly one outgoing arc. It uses subcycle elimination constraints to ensure that in each subset S, there is no subcycle in the subset. However, this encoding requires an exponential number of clauses to encode. There are several n-cube encodings which deal with position variables in different ways. However, these encodings suffer from code explosion problems, and they are unable to encode the Knight's-Tour problem for large sizes. Recently, Andrew Johnson proposed an encoding called LFSR encoding, which is very compact, uses log encoding for position variables, and uses linear feedback shift register to generate the next position. This encoding is able to solve the Knight's-Tour problem for size 22, but does not scale well. So in this study, we compared the three encodings for the successor function: Unary encoding, binary encoding, and this LFSR encoding. And we propose techniques for improving these encodings, including a hybrid encoding for the at most one constraint, which is used in degree constraints, and logic optimization for log encoded position variables, and an optimized incrementer for this arithmetic addition, and also preprocessing techniques for excluding unreachable positions from position variables. So our study finds out that the improved binary encoding is the best. It is able to solve all the Knight's-Tour problem instances for some sizes that had been unreachable for set solvers, and it also performed the best on the HCP instances used in the XCSP competition. All right, now let me talk about the details of this research. So for the global constraint, like the Dantzig's IP model, we use a matrix of Boolean variables H, to encode a cycle. So Hij equals 1 if the arc ij is in the cycle. We map each vertex into a unique position, so we use this function P. And we also use the successor function SP, okay, for the successor of P. And we apply the successor function K times, okay, we denote this as S to the power of K. And we use constraints, first channeling constraints, okay, to connect the original problem variables and the variables H. So this Hij, okay, so is true if and only if Vi is assigned the value J. And okay, these channeling constraints ensure that each vertex has exactly one outgoing arc, because each domain variable can be assigned only one value. And we need degree constraints to ensure that each vertex has exactly one incoming arc. And where there are constraints on position variables, okay, first, this vertex I is visited first, so vertex 1 is mapped to 1. And for each non-starting vertex, okay, I, if I is visited after vertex 1, okay, then I's position is the successor of 1. And if I is visited after vertex I, okay, then I's position is, okay, so the A minus 1 successor of 1. And we also have transition constraints to ensure that the positions are connected. All right, we consider three encodings for the success function: the unary encoding, binary add encoding, and this LFSR encoding. In the unary encoding, we use a Boolean variable for each vertex and each position. So UIP, which is one if position. A vertex I is mapped to position 1. And we're in the binary add encoding, we use log encoding for position variables. And we use this binary adder, okay, to generate the next position. Okay. In the LFSR encoding, okay, we also use log encoding for position variables, and we use this, okay, special circuit, okay, to generate the next position. In the unary encoding, the transition constraint is encoded as follows. All right, so for each vertex I and each vertex J and each position, okay, if Ij, okay, is connected, okay, and I's position is mapped to is P, okay, then J's position is P plus 1. Okay, this encoding, all right, requires this order number of clauses, okay, to encode. The binary add encoding, okay, so we use log encoding the domain variables, and the transition constraint is encoded as follows. For each vertex I, vertex J, okay, if I and J are connected, okay, then J's position is I's position plus 1. Okay. And so this is a crucial constraint in this encoding, this add 1 constraint. All right, so it is very important to find encoding, efficient encoding for this incrementation. Also, giving a binary string, okay, we add 1 to it to generate the next position. Okay, for the lowest 2 bits, okay, so for the lowest bit, what do we do? Okay, we know x0 and y0 are complementary. Okay, this constraint can be encoded using 2 clauses. For the second lowest position, x1, okay, we dispatch on the value x0. If x0 is 1, okay, then there is a carry, okay, from the lowest bit. So if x0 is 1, okay, then these two are complementary. And otherwise, okay, these two must be the same. Okay, so these 2 constraints require 4 clauses to encode. And for other bits, for each of the other bits, okay, we would do, okay, if there's a carry, okay, then these 2 are complementary. and otherwise these two are the same. Okay, this one for each bit, okay, we need 6 clauses. Actually, we could do better. Instead of considering 1 bit a time, we can consider 2 bits a time. So if there is a carry, okay, from bit I minus 1, okay, then these two are complementary. Okay, if there is a bit from I, okay, so then these two are complementary. Otherwise, okay, xi equals yi equals xi, and okay, they are the same. So this one, okay, can be encoded in using 11 clauses, okay, which results in one saving of 1 clause for each 2 bits. Actually, we could do better. For the topmost 4 bits, okay, we can use a special circuit to do incrementation. Alright, this one, okay, uses 21 clauses. If we do it 1 bit at a time, we would need 24 clauses. Okay, that gives a saving of 3 clauses. Okay, for these 4 bits. Alright, this LFSR encoding, which is very similar, except that it uses a special circuit to generate the next solution, next position. All right, so this one is so giving a binary string, it generates okay the next position. So let's say okay, consider this a 4-bit circuit, and it does shift. So it gets y3 equals x2, y2 equals x1, and y1 equals x0. And for the lowest bit, okay, it chooses 2 bits as tabs and takes the XOR of these 2 tabs. In this way, it can generate all these non-zero values. All right, we consider preprocessing. So we can treat HCP as a single agent pathfinding problem. So at time 1, the agent resides at vertex 1. So in each step, the agent moves to the a neighboring vertex. All right, we can use path constraint heuristics. Well, basically, at time 1, the agent is at vertex 1. And at time n plus 1, okay, the agent must be back at vertex 1. So if there is no path, yeah, if a vertex cannot be for each vertex and each time, if the agent cannot reach that vertex at that time, okay, then we can exclude that position, yeah, from the position variable. Okay, that's the basic idea. Okay, so of course, for large graphs, okay, we cannot afford finding paths of a certain length. Then instead of finding all paths of a certain length, we can use shortest distance heuristic. All right, there is another technique which is similar to the host theorem. So if the start vertex 1 has exactly 2 neighbors, okay, then the agent must visit one of the neighbors at time 2 and visit the other neighbor at time n. So the nice tool problem, okay, falls into this case if the start vertex is one of the corners. All right, we implemented all these set encodings in PyCat, and the PyCat, the default encoding is the binary add encoding because it performed best, and we evaluated these encodings, okay, using 2 sets of benchmarks: the nice tool problem and also the HCP instances used in the XCSP competition. Okay, in addition to the set encodings, we also included in this comparison the Klingos ASP solver and then this O2's CP solver. We also included in this comparison incremental set solver, which incrementally uses generates subcycle generation elimination constraints. All right, first, okay, this table shows a comparison of these encodings on the number of variables. All right, basically the results is consistent with the theoretical analysis. If no pre-processing is used, okay, then there's a binary add encoding and there's a LFSR encoding, okay, uses the same number of variables. And with pre-processing, however, okay, the binary add encoding uses slightly fewer variables. Okay, this is because of logic optimization. Okay, the position variables are minimal, okay, to logical optimization, okay, with processing. Okay, and the unary encoding uses much more variables. And this table shows the number of clauses, okay, in the generated code. Again, so this LFSR is the most compact encoding, and followed by the binary add encoding, and then the unary encoding. All right, this table compares the runtime, the encodings on runtime, solving time. The binary add encoding, okay, so interestingly, the binary add encoding performed poorly, yeah, without pre-processing performed poorly. However, with pre-processing, the binary add encoding solved all these instances, okay, very quickly. It performed best, okay, with processing, pre-processing, it performed the best. Okay. And well, for these instances, okay, you know, CP solvers perform really faster. Okay, so does the ASP solver. Okay. And this table shows some of the instances that solved by the binary add encoding. Okay, these instances were beyond the reach of set solvers. All right, this table shows CPU time on the HCP instances used in the XCSP competition. Again, the binary add encoding, okay, all of them, okay, all of this includes pre-processing. The binary add encoding performed, okay, amazingly well. It outperformed not only other set encodings, okay, but also the O2s and also the ASP competition, ASP solver. So, in conclusion, this study has found surprisingly, okay, with optimizations and pre-processing, the binary add encoding significantly outperforms the unary and the linear feedback shift register encodings. Okay, and a lot of future work to do. So, for example, although for some of the instances, for some of the used in the competition, this binary add encoding is competitive with CP solvers, and it performs poorly on the nice tool problem. Okay, you know, CP solvers can easily solve nice tool problems. Okay, for size 50, and it remains an open problem how to solve nice tool problems for big sizes. And also how to solve the traveling salesman problem, which is a more general variant of the Hamiltonian cycle problem. Okay, thank you.